atoms of light elements are squeezed under enough pressure for their nuclei to undergo fusion. All stars are the result of a balance of forces. The force of gravity compresses atoms in interstellar gas until the fusion reactions begin. And once the fusion reactions begin, they exert an outward pressure. As long as the inward force of gravity and the outward force generated by the fusion reactions are equal, the star remains stable. Clouds of gas are common in our galaxy and in other galaxies like ours. These clouds are called nebulae. A typical nebula is many light years across and contains enough mass to make several thousand stars the size of our sun. The majority of the gas in nebulae consists of molecules of hydrogen and helium, but most nebulae also contain atoms of other elements, as well as some surprisingly complex organic molecules. These heavier atoms are remnants of older stars, which have exploded in an event we call a supernova. The source of the organic molecules is still a mystery. Irregularities in the density of the gas causes a net gravitational force that pulls the gas molecules closer together. Some astronomers think that a gravitational or magnetic disturbance causes the nebula to collapse. As the gases collect, they lose potential energy, which results in an increase in temperature. As the collapse continues, the temperature increases. The collapsing cloud separates into many smaller clouds, each of which may eventually become a star. The core of the cloud collapses faster than the outer parts, and the cloud begins to rotate faster and faster to conserve angular momentum. When the core reaches a temperature of about 2,000 degrees Kelvin, the molecules of hydrogen gas break apart into hydrogen atoms. Eventually, the core reaches a temperature of 10,000 degrees Kelvin, and it begins to look like a star when fusion reactions begin. When it has collapsed to about 30 times the size of our sun, it becomes a protostar. When the pressure and temperature in the core become great enough to sustain nuclear fusion, the outward pressure acts against the gravitational force. At this stage, the core is about the size of our sun. The remaining dust envelope surrounding the star heats up and glows brightly in the infrared part of the spectrum. At this point, the visible light from the new star cannot penetrate the envelope. Eventually, radiation pressure from the star blows away the envelope and the new star begins its evolution. The properties and lifetime of the new star depend on the amount of gas that remains trapped. A star like our sun has a lifetime of about 10 billion years and is just middle-aged, with another 5 billion years or so left. Margaret M. Hansen, an assistant physics professor at the University of Cincinnati, gives this response. Stars form from the gravitational collapse of large clouds of interstellar material. In fact, the space between stars is not empty. It is nearly empty, but not entirely. Interstellar matter, that found lying between the stars, is made from gas and dust. Granted, only about 10% of the mass in our Milky Way galaxy is made up of interstellar matter, but this material, as tenuous as it is, exerts a gravitational force, and as a result, it will begin to pull itself together. As this accretion continues, the gravity becomes increasingly strong because its strength rises as the mass increases and the distance of the individual atoms decreases. Eventually, this interstellar matter entirely collapses in on itself. The material at the very center is compressed by the involving material on the outside, pushing down to get to the center, and this compression heats up the center of the collapsing cloud. At some point, the temperature gets so extremely high at the center it triggers a fusion reaction. All the material that has fallen in then evolves into a hot, bright star. The star will continue to shine as long as there is hydrogen gas to fuse through nuclear reactions, and the gravitational pressure pushing inward keeps the atoms very hot and tightly packed at the center. Originally published Scientific American Online, December 6, 1999. How long do stars usually live? John Graham, an astronomer at the Carnegie Institution of Washington, explains. The length of a star's life depends on how fast it uses